Welcome to the October 2024 indoor meeting of the Raleigh Astronomy Club. So I'm not going to bleed this slide out. If we have any new members or guests, I've tried to walk around and speak to all of you. If we missed you, it's not intentional, except for Blair, that we ignore you or anything. But please introduce yourself. Let us know that you're here. We're going to hold questions until the end, so that Tom can just speak through his presentation all the way. Okay. We do have a microphone that we have to pass around, because if you don't have the mic, Tom can't hear what you're asking. So if I make a noise like while you do it, then please don't. So please note that there are room hazards around. There's extra chairs. There's a trash can over there. There's a rug in the back. We got cables and stuff. So please be very, very careful. Yeah. It's a low light room. So anybody CPR trained? Okay. That's a little scary right there. I think I need an emergency caller. Blair, you got a cell phone on you? Okay. Can you call 911? Okay. Okay. Fire equipment, in case anybody feels like fighting the fire. There's a fire extinguisher right under the clock over there, kind of around that corner. Okay, remote attendees, please be aware of your surroundings. So we don't want anybody at home getting up and running around and falling or anything. This is our evacuation route. Out the door, the stairs. Don't get in the elevator. And we've quit again. Oh, there we go. That's yours, Susan. Did you want to say anything? Okay, logbooks are here. And she's going to be at the RAC barbecue tomorrow. Okay, I'll just bleed these out. Willard is the night before Halloween. Thank you. We have a RAC class coming up, imaging workshop. The topic has not been determined yet. Morrisville Community Library is on the 7th, on the 8th, first Fridays. So there's a really nice thing about this. If you look at November 8th, you'll know what day the next rainstorm's coming through. Okay. Stargazing on tap in Cameron, November the 9th. I don't know. Steve's not here, so I don't know. I can't expand on any of these. STEAM night, Salem Elementary School. Absolutely. Okay. So the next meeting of the Astronomy Club Indoor is November 15th, and it got left out of the slides. Oh, sorry, I didn't realize that was there. The November 23rd is Prairie Ridge, but it's joint with the Moorhead Planetarium. I thought there was another one about Moorhead. Okay, and then December 6th is the next rainstorm, 3 Bear Acres, and the Willard is on the 18th. February 8th, astronomy night at Joyner Park. Okay. We have our barbecue tomorrow. If you haven't signed up, I'm sorry. But please bring a side if you're coming. Susan, do you have anything to add? Anna? Chris? Bueller? Okay. So tonight's presentation is from Tom Fields. You can almost touch the stars, an introduction to astronomical spectroscopy. So Tom was a contributing editor at Sky&Telescope magazine for 10 years. He's the founder of Field Tested Systems and the author of RSpec software, which received the Sky&Telescope Hot Product Award. He's a pioneer in the field of amateur spectroscopy. Tom aims to demystify the field, make it accessible to all. He promises to open the door for you to this field. So we have to switch Tom and let Tom chair. And once we do that, we'll be in for his presentation. Yeah.
Okay. Corky, can you shake your head yes if you can see that prism? Thanks so much. A wave hand is good too. Good evening, everybody, and thanks for coming. I see the people there in the room, and also people who have dialed in, dating myself with that verb. I hope we'll have some fun tonight and you'll come away interested in having learned something. So I'm looking forward to it. We'll take questions at the end, as you heard. That's where you'll really get to discover how little I know. We'll talk a little bit more about how I'm so able to fake it as we go through the talk tonight. So, this is that iconic view that we get to see, and it's been around for a bunch of years now. The thing is, I always wonder about all the other stars in this field of view. Give me just a second while I get my mouse working. Excuse me. Some sort of malfunction here. So let me come over here and try that again. There we go. So it's all these stars over here, and not the beautiful stars we focus on, but don't you think they may feel a little bit left out? So, you know, I'm nowhere near that tower. I like to look at towers like that. I'm probably somewhere over here, behind some small window. But for many years, I've wanted to know more science about the stars. I was an imager, did, of course, like a lot of us, a lot of visual imaging, but I never really feel that I got a good fundamental understanding about what was going on. Because most of us, including especially me, go about this haphazardly. So how is it that we can all go about learning about the stars? Of course, there's a lot of different ways we can do that. And I've tried most of them, and I pick up little bits and pieces, but none of it really sticks with me, and it's just never been all that sticky in my mind. So I want to show you just an example of two of the kinds of things we're going to be looking at tonight. So this is, of course, our beloved Orion Nebula with its belt stars, and there are the three belt stars. And when we split that starlight, and I'll show you how we do that in just a moment, we can see that each star has its own spectrum. Now, of course, there's a lot of other stars in that field of view that are projecting spectra. We're just going to look at these three. And as another example, I wanted to show you this star field in Perseus. Is this an interesting star field? I'd say no. It's a bunch of dots, these stars get in the way of our deep sky object observing and imaging. But every one of these stars has a story to tell. And right now, we're going to look at just three of these stars to give you a flavor for what we can learn. Now, my background is I'm not an astrophysicist. I don't have a degree in science. I'm just a guy. I'm a knuckle-dragging guy. So I'm going to try and sound like I know what I'm talking about, but I'm going to confess before I start that I'm telling you just about everything I know about these stars. The beauty here is that we get to decide how much we want to learn, and a tool like this helps us do that. So let's look at this wide field. Now, this was captured, and I'm going to emphasize this repeatedly tonight. This was captured with just a DSLR. So we don't need a lot of aperture. And also, a lot of what we're going to see tonight was done near big cities. We don't need to go to some dark sky site. And I'll talk a little bit more about that as we move forward. But if we look at these three stars, and once again, I'm already off to a good start. If we look at these three stars, let's just start with this star here. So this star has a spectrum that's there. And we can see in that spectrum, there's some gaps, right, in that rainbow. Now, how we create that spectrum, we'll look at in just a few minutes. But those gaps tell us something about that star, where it is in its life story, its size, how it's moving. We're going to not get into a lot of the science tonight in terms of how spectra are produced subatomically. That's over our heads. But what I did want to show was just that each element has its own spectrum, and we'll come back to that. So now, many of you may be aware that, of course, we classify stars by temperature. The cool stars are over here, the hot stars are over here, And this is just one dimension of a map. Now, I have a really quick story. My wife years ago was out doing an errand, and she used her GPS phone and Google Maps to get where she was going to the strip mall. And when she went to leave, she didn't have Google Maps turned on, and she realized she had no idea which way to turn to get out of the parking lot to get home. She was out of her usual area. And I use that as an example for the fact that we all need maps, whether they're physical maps or whether they're cognitive maps. And many of you may be familiar with this diagram here. We're not going to talk about it a lot, except for me to point out a spot or two on it. There's a lot in this. The reason I want to point this out is because the star that we were just looking at is one of these cool M-type stars. It's actually up here. It's a supergiant. It's a big red star, but it's very cool. So we've just visited somewhere on this map. And my conjecture, my assertion tonight is when you have a map like this, then the reading that you do online, in books, wherever, becomes more sticky, because now you have this literally physical layout that you can start attaching things that you're reading to. Now, I'm not a cognitive scientist, so this may all be BS. So I'd like to look at for a moment at this star here. It doesn't have those gaps like that gap up there, but it has this really bright spot. What's going on with this star? Well, it's called a BE star. It's a hotter star, but that E stands for emission line. The disk of dust around this star, and not every star has this kind of disk, is glowing. So that's called a BE star. And if we look at our HR diagram, if I can get my mouse to work, we can see over here that the B stars are more down around here, right? So this is a star that's up in that area. So we've visited two different quadrants. Let's look at one more example and then we'll dive in. And that's this star that's down there, the Wolf-Rayet star, it's called. Look how its spectrum differs so much from the others that we've already seen, with a lot of bright spots. Now, by the way, what I'm showing you is the way that we understand 70 or 80% or so of what we know about the star. So even if this is something you don't want to do ever, maybe you don't have a telescope, or I'm not successful in convincing you tonight that this is something that would be fun and easy for you to do, I think you'll find that you get a good sense for how professionals and amateurs use these tools. So what is this Wolf-Rayet star? Well, without getting into a lot of details, it's a star in the later stage of its life that's blowing off its outer shell, and we're seeing that glowing dust. That's what all these dots are down here, are glowing points in that star shell. Now, we can dive more into more detail, and this is typically the way I've been learning, is I'll capture the spectrum of a star, or maybe read about a star first on Wikipedia. And then when I have both the data and the image, it becomes more interesting. Look how hot these stars can get. We won't get into a lot of the details here. They've got strong stellar winds. I'd read about stellar winds for ages, but when I captured a spectrum that had the stellar wind in it, it really helped me understand and remember. So these are really hot stars, so they're somewhere probably over in this area. So you can see the HR diagram can be really helpful in classifying what we're observing. So here's what I'd like to get out of this talk. What I'd like you to get out of this talk. What I get is the pleasure of sharing something that I've helped literally thousands of people get started in. And I have countless emails here on a different screen where people go, oh my God, I can't believe I'm doing this. I never thought it would be this easy. So the key that I mentioned earlier was it can help you understand about the stars. And it's not hard to understand how to do it or the background of how stars do what they do. And it's easy to capture spectra, and it's really inexpensive. So, and as I mentioned earlier, it's much less susceptible to light pollution for reasons we can go into if you care during the Q&A. So how do we capture these spectra? Well, we use just an 1.25" grating. It's like $200. It's a star analyzer grating. And I'm going to demonstrate it here for you just so you can see. I don't have a star, but I have got this gas tube. I hope you can see in the participants window. that gas tube turned on now. And now I'm going to take this grating and just hold it up to my camera. Can you see all those spectra there just repeating across? That's what we do on a telescope
Hold
with
on.
starlight. Yes. Yeah.
You need to quit sharing if you
Oh,
want.
okay. Would that be easier for you? That's terrific. I'll do that. Thanks for jumping in. There we go. Full screen. So there's that gas tube. And there's that spectrum. You can see it's repeating across the image there, but there it is. Got to rotate it around. That's what we do with stars. So this is the kind of thing that you can do from your backyard. And that's my background. I'll talk a little bit about that in a few minutes. So let me share my screen again. We'll go in and out of screen sharing just a handful of times tonight. There we go. There's that. And I'm going to come up here and go like that and get back into my PowerPoint show. Now, what do you do with this grading? Well, almost any camera, could be a DSLR lens. We have a little adapter for it, standalone. It can be a standard fits camera. Now, an important thing I want to mention is it can be a mono camera or color. Color is, again, like in visual imaging, not as good, but it's also a lot more intuitive, as you'll see shortly. You can put your DSLR on a telescope. You can even capture videos. And live, you can look at spectra. I have a really cool video of Alberio, which maybe we'll have time to look at tonight. And you can put it in a filter wheel. So there's any number of ways to mount spectra, to mount a star analyzer grading. It's less than the cost of a good eyepiece. So just a really brief bit of history here to give us some context. Sir Isaac Newton is said to have been the first person to split starlight or split light, white light, into its colors. You can also bounce light off a finely lined surface, or like with the star analyzer grading, this has a whole bunch of lines in it. Really, how do you like that for a technical term? Whole bunch of stars. Very finely lined device. So Bunsen invented the Bunsen burner to burn a sample, look at it through a prism, and study the results. Many of you may have used or heard about Bunsen burners in chemistry labs. Here's an interesting factoid about Bunsen, and that is he deliberately and explicitly announced he was not going to patent the Bunsen burner. He wanted it to be available for the future of humanity. Now, of course, today he might have sold it to a corporation, a private equity, made a lot of money and had it locked down. But it's great that he did what he did. Now, I'm not going to talk much about Kirchhoff. Our time is limited tonight. But I wanted to revisit this slide one more time to talk about hydrogen as an example. Here's its spectrum when we look at it through a gas tube or through a star analyzer. Now, these lines are so common, and hydrogen is so common, we actually have given them alphabetic Greek letters. So that hydrogen beta there, what color would you call that? Let's call that robin egg blue as a technical term. But we'll come back and we'll see why I want to identify that in a minute. So we're not going to get into all the chemistry of all 100 and some elements, except I wanted to point out on this chart, on this periodic table, there's hydrogen, very different than helium, right, in spectrum. There's that robin egg blue hydrogen beta line that I mentioned a moment ago. This is a poster that I created some years ago. We saw a lot of them to schools and some to amateur astronomers too. I wanted to talk just a moment about the great astronomers in the world. The astronomers I've mentioned so far, Kirchhoff, Bunsen, although they weren't specifically astronomers, but what do they have in common? Well, they're old white men. I want to talk about some of the others in our field. Annie Jump Cannon, you may have heard of. She and her team of women computers more than 100 years ago were prohibited from accessing the Harvard telescopes. So they studied spectra. That's what she's doing there. And that's what all these plates are. And they classified hundreds of thousands of stars from their spectra, came up with a classification scheme that serves us today still. Priyamvada Nataraja was at Yale studying black holes. I'm going to move quickly. Nancy Grace Roman was the first astronomer at NASA, a woman astronomer in the late 1940s. Think of the challenges as well as the strength that she showed to succeed in that environment. Jedediah Eisler was at Dartmouth studying hyperactive black holes, and Elisa Quintana studies exoplanets around cool stars. So there's the first star, the first star that we discover with an exoplanet around a cool star. I don't know if you can read this from where you are. It says where the grass is always redder on the other side. On a red planet, on a planet around a red star, we might see red grass because the photosynthesis wouldn't be green, it would be red. It's a fun poster from NASA. All right, let's move on here. And now that we've talked a little bit about those items, what can we actually do? So we take the starlight and somehow mount it on a camera. It goes through our star analyzer grating, and some of the light is bent like a rainbow in a prism. And then this would be our sensor. We would see this in our image. There's the star, there's the spectrum. Let's look at this just brilliant image here. So very pretty. These are a series of images captured by Torsten Hansen with just an 8-inch Newtonian and a video camera, one of the older models. Each of these is a different spectrum. These are the hot stars here going all the way down to the cool stars. So these are B stars and M stars, if you're familiar with that nomenclature. Look at the differences in the spectra for those different stars. Two quick examples is all we have time for. Notice those broad bands of darkening, of absorption features. Well, these cool stars down here are cool enough that on the outer shell of that star, there can be some complex molecules that absorb starlight. And I'm going to tell you everything I know about them. They're called titanium oxide. Titanium dioxide is used in suntan lotion. One more example here, and that is up here, notice that dark line on all these hotter stars that doesn't even exist down on these cool stars. That's that robin egg blue line that we talked earlier about. That's hydrogen beta. So you can see, let's just step back so we don't get lost in the forest. What we have here is a tool that lets us really easily detect the composition and the temperature of stars. It's an incredible feat that humanity has pulled off in just a little more than a century. It's really amazing. So a quick review of how these lines are formed. This is all the deep detail we're going to get into. As a reminder, the Bohr model of the atom that we studied has shells around which electrons orbit, and they're numbered. And when an electron jumps from shell 1 to shell 4, they absorb light in this region, in the hydrogen beta wavelength down here. That's it. So different transitions in here produce different lines over here. And that's what we're going to be looking at tonight. Not how it happens subatomically. We don't need to know that. If you want to, have at it. All right, so one thing you may have already noticed, and that is that sometimes we see gaps in a spectrum, and sometimes we just see bright lines with just black in the background. I'm not going to get into a lot of detail about this, just so you know that's the case. It happens depending on gases between us and the star and things like that, but it's not necessary to understand how it happens. So I don't know if on your screens you can see that right in that crosshairs is a little bit of dimming. Suppose the Hubble Space Telescope people made an enormous mistake and gave me some time on the Hubble telescope, and I came back with this image that you can see there with the crosshairs, and I wrote a paper and I said, yeah, there was a little dimming in the robin egg blue. They'd be sure they made a mistake, right? So in order to do science, we have to quantify this data. And the way we do that is by creating a graph of this area, between my arrows here. It's an intensity graph. So this is just how bright is that area. So this high peak is because the star is really bright. And this data over here is of this region, dimmer in the wings on the ends and brighter in the middle, right? Dim, bright, 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 dim, dim, dim. And when we graph the data, look how clearly that absorption line shows up, that dip. So how do we create a graph like that? Well, that's where my story comes in. I got a grating like this in 2009. And I went out in my backyard here in Seattle with my C8, and I came in at midnight in August. I had grass stains on my blue jeans. I was looking at Vega overhead. And I was using a Logitech webcam with 2-star diagonals duct taped together with the camera. And the next morning, this is that first image I caught. The next morning, I wanted to create this graph and I couldn't. I'd struggled with some of the shareware that was out there at the time. And not only was it crashing a lot, but to add injury to insult, the error messages were in French. So that software has improved a lot since then, and the authors of that are now friends of mine. But I gave up. I was so frustrated. You know what it's like learning new software. Try learning software. You know there's some out there, some of you know, that takes a week worth of workshops to go through. I wasn't up for that, and I couldn't find software that did that anyway. So I figured, okay, next weekend I'll write a piece of software just to create the graph. And I did, and it worked. And now 15 or 20,000 hours later in programming, it's almost done. I'm close. My wife keeps saying, would you finish the software? So this is an example of another star field I wanted to show you. It's out of place in my show, but again, in the Pleiades, you can see every star in the Pleiades has its own story to tell. But there's my software, and you can see there's a gas tube like the one I showed you. There's a spectrum. There's their robin egg blue. But what I want to do, I do want to jump out for a moment to show you my software. Now, if you don't see my software screen right now, Corky, wave at me. There we go. So he's not waving. He either can't hear me because I'm muted. There. Thanks. I gave you bad instructions there, Corky. My bad. So this would be an image from your telescope or your DSLR. It could have other stars in the image. In this case, it's a PNG file. It could be a FITS file. It could be a live video stream. It could be a mono file. I like, as I mentioned earlier, the color. You can see there's the star and there's its color spectrum. If I'm doing outreach, and what I'm going to show you is a great outreach tool. You can do live video streams of this, almost anywhere the club's doing outreach. And I know your club does a lot of outreach. So again, thank you all for that. So I don't know if you can see, even right there, we can see that absorption line. Let's zoom in. Yeah, see it there, and see there's one there and there. We can't see it with a bare eye in the eyepiece of our telescopes. With a camera, we can capture it. And then all we do is drag these lines around the region we want to sample. And then over here, we have that intensity graph. This peak is from the star, right? So this is relative flux or brightness here on the x-axis or y-axis. And this down here is wavelength. Look at all those absorption dips. So that one in the robin egg blue, if we come over here, is that one. Look how deep and clear that is. You would never expect that you could see that kind of thing. And there's lots of others here too. Okay, last step is like, so what? There's a bunch of dips. How do I know what they are, Tom? Well, we typically go out and look at things and we sort of know what we're expecting. And so in this case, this is Castor. It's a particular star. It's not too cold, not too hot. And I can ask the software, overlay on the graph where I would see absorption lines if this was hydrogen. And look at that. Let's zoom in on that because it's just pretty cool. There we go. So everywhere my data, I expect from this reference overlay to see an absorption or a dimming in my spectrum, we're seeing it. We've now detected on Castor with a backyard telescope 3 miles from Pike Place Market in downtown Seattle, we have confirmed the hydrogen on that star. That's what this is about. I'm not going to spend any more time here because I know that, especially at this hour there, I'm in Seattle, as you heard. At this hour there, if I go just another minute or two, I'm going to start hearing heads thump on microphones that are unmuted as you fall asleep. I know I would. Software demos are boring. So one thing I might mention, though, since I'm there, and that is the software comes with a video library. It's on our site. You can look at it anytime you want. The videos aren't 4-hour workshops that you have to attend. They're 4 or 5 minute little clips that you can look at, and I narrate and show things just like I'm doing here. So let's go back to our PowerPoint show and continue. There we go. So just in passing, I might mention that if you're an educator, we also sell a little classroom device like this to use on gas tubes. It's quite popular. We've got a lot of schools using it. We developed some labs with a variety of universities, including UNT down in Texas. Here's the kind of thing you can do at a star party. This is in Marseille, France. Maybe you can see the French there. You might not want to do a bright screen like this at a dark sky site, but you can show spectra and get a lot of interest. So let's start looking at a handful of examples. We're not going to go on forever, but I want to show you a handful to give you a flavor for what you can do. This is our beloved M57, and if we put a star analyzer on the data, we see two emission lines. We see two bright lines of the hydrogen and the oxygen. Now, again, there's tons of books I'll be mentioning later that help us understand what we're seeing. This is with a star analyzer. Most extended objects, other than this, we have difficulty capturing spectra of. Star analyzers, because they don't have a slit, are intended for compact light sources. Let's look at what a slit device could do, just so you know what you're getting into. These are the typical prices of slit devices. They're also considerably harder to use. There are some DIY 3D printed devices, but literally, I know of 2 or 3 people out of thousands who have started this way. It's a pretty big step to start. But let's look at a spectrum of another beloved object of ours with a slit device, M42. We can see the same peaks here, even though it's an extended object, right? It's the birthplace of stars. And by the way, I meant to mention in the beginning, you know, if I'm starting to put you to sleep, even though there are acknowledged hazards in that room, you know, no hard feelings on my part if you take off. You know, I'd rather you not be polite and take off. I don't want to, you know, sort of have you feel like you're stuck here. What a buzzkill to say that in the middle of the talk. I'll try and avoid it in the future. By the way, Corky, can you actually see my face now or just the projection screen? You can see my face too? Okay, well, I'll keep looking into my camera and emoting. So this is the Orion Nebula, but you know, I wanted to take a break. You heard earlier, I was a contributing editor at Sky&Telescope for 10 years. You know, the magazines accidentally mislead us. Remember back before you were doing any of this? Maybe you saw a beautiful picture of M31 or some other colorful object, beautiful object. And you thought, I want to get me some of that. That sounds like it would be fun to do. And then you found out as the years went by that it's not so easy, is it? So a lot of those images that we see in the magazines, you read the fine print and it's like, well, this is 40 hours of integration time on a mountaintop with a, you know, 32-inch telescope and, you know, 6 hours of processing time. I don't have the time, the money, the interest, the skill, the equipment, the location, any of that. 40 hours, sometimes here in rainy Seattle, that's my entire observing season added up for the whole summer. The reason I tell that story is because I want to assure you this isn't a bait and switch that you're seeing here. What I'm showing you in these slides is things that you could do, not the slit stuff, but everything else with the Star Analyzer, you literally could be doing them tomorrow night. I've had high school students do this their first night out. If it takes 2 nights, that's fine. Who cares? It's 2 nights. It's not 20 years to get to the point that you want to get. You're getting interesting and exciting data right out of the gate. Okay, so let me get my mouse over here and look at this other example. This is Uranus. Look at those deep methane absorption bands that we're seeing. And when we discover ET, I had some fun ET slides here that I took out for time's sake and because they were a little goofy. When we discover extraterrestrial life, assuming we do, it's going to be with spectroscopy. We're going to see features like this methane on Uranus with a backyard telescope. Look what Bodkin did, 4.5 inches and a video camera. Okay. In 1881, Henry Draper captured the spectrum of a comet, and the New York Times felt it was important enough to document. Heck, if Hank can do it, so can we. So over here, we have the spectrum in my software. By the way, I haven't mentioned it. I'm a bad marketer. RSpec Astro. You're sort of stuck with it in your face in the footing there, though. There's the spectrum, this little string of gems. They're called the swan bands. Even though comets are a little bigger than a compact point star, they often have a compact core that we can capture the spectrum of. Look at what Vikrant Agnihotri in India did to capture this. He was using just an 80mm refractor, a star analyzer, and a Canon camera. It's amazing. Okay, here's another image of spectrum of a comet. I wanted to show this just so you can see some of the other features. Now, I didn't know what any of these things were. What Na, sodium, line, D lines, whatever. That's where the books that I'm going to talk about come in. They're not big 3-inch thick textbooks with a lot of math. We'll see that in a moment. So, what about the spectrum of a meteor? Here's our star analyzer on a video camera. This is all captured by Robin Leadbeater, a leader in the field, been a big help to so many of us, including me, and the designer of the star analyzer. The thing is, he used, and I love it, this do-it-yourself C-clamp. If it was me using a C-clamp, it's likely I would over-tighten it and it would end up collapsing my camera enclosure. This was years ago that he did this, but look at this spectrum down here. This thing here is the meteor, moving in that direction, and this is its spectrum. Right there was a brightening, some sort of bolide, and here is just tentatively identified the spectrum of that region. So if spectroscopy is a niche, then this is a niche in a niche, but it's doable, and whatever floats your boat, right? I'm not going to spend much time on the sun. We've had a lot of solar eclipses in the last handful of years, but you can do great solar spectroscopy with a star analyzer and just a DSLR. Quick review as we do just a few more examples. Just a reminder of what Doppler shift is for those of you who may have forgotten. It's the change in pitch that you hear as something is moving towards and away from you. So a train coming through a station, right? High, coming towards you, low, going away. You can actually hear that just from the hiss of cars or trees as you're driving on a road, not very fast, right? The trees go, phew, phew. That's a bad example. But I went the wrong way because I wanted to show you this triplet. Self-defining word, nice word. If we were expecting to see a triplet like that in a spectrum on a star, and instead we saw it over there to the right, we would know that it was redshifted and the object was moving away. And of course, if we saw it over to the left, we'd know the object was coming towards us. How can we use that on a backyard telescope? Well, this will be the shortest description you've ever heard of a supernova, a particular type of supernova. There's two stars orbiting each other. One's big. Some of its gas gets drawn in with the small one, and when you throw gas on a fire, sometimes it explodes. Type 1a supernova. Fascinating events. Here in M101 is a supernova. Huge galaxy. There's the supernova. And this is a video of a supernova going off. That's a little eye candy. But also I wanted to show you this expanding shell because that's what we're going to study. Here's an image of a supernova from 1987. This is a real one, but not the one we're looking at here. And you can see that shell very clearly. So David Strange, with just a 9-inch SCT and less than 15 minutes of integration time, so there is some stacking going on here, was able to capture this spectrum and detect that dip. See that dimming there? Well, it showed up as a deep dip. Now, the next slide isn't going to be on the quiz I'll be giving at the end here, but there are different types of supernovae. Some of the stars run out of fuel, but the one we're looking at here has a deep fingerprint dip. I haven't used that word fingerprint yet. I should have much earlier in my talk, because every star type has its own fingerprint. Every element has its own fingerprint. But this dip here at about 6,000 is silicon. That's all I can tell you about silicon and supernovae, but you can read more about it. And the reason I keep bringing that up is I think the biggest inhibiting factor for any of us getting started in this, including me, is the thought, I don't know enough to do this. How am I going to learn all this? So I want to show you something really cool here. There's that dip, right? It's down around 6,000. I want to show you just addition, subtraction, and division. No higher mathematics. Even I can do this. How fast is that shell expanding? Well, let's take that number from the x-axis and record it. And then we can look up where that line would be, where silicon would glow if we burnt it stationary here in the lab. Maybe we burnt beach sand. You can see those two numbers are different. That's the Doppler shift. So I couldn't remember the Doppler shift formula. Wikipedia is my closest friend sometimes, nerd that I am in my man cave like this here. So you plug the numbers in, and you calculate the speed that that shell is coming towards us with a backyard telescope. There should be a couple wows. First of all, wow, that's fast. And secondly, wow, I can't believe I did that with a backyard telescope. So a lot of what we do here is duplicate the results that other people have gotten, the professionals with much bigger telescopes. You may recognize this name, Adam Rees. He won the Nobel Prize in 2011 for the studies that he and his team did at the end of the last century on the accelerating cosmological expansion. I think he used equipment a little more sophisticated than a star analyzer. It's pretty cool that we can do the same kind of thing and measure that, in this case, the Doppler shift of the shell, not the cosmological expansion. I don't have time in the body of my talk to tell a quick story about him, but he commented on this next spectrum that I'm about to show you, and that is, what about the spectrum from a black hole? Well, a black hole doesn't emit light, but the circumstellar, the accretion disk, it's not stellar, but the accretion disk that's spiraling in gets very hot, and it creates emission lines. Let's take a look at a spectrum. Now, you, of course, all know, you can see where 3C273 is in that star field, right? Well, I couldn't either, but David Hayworth, who captured this image, knew where it was. And there's its spectrum with two little bright dots. Let's zoom in on that. Backyard telescope again, we're talking here. And we can see those bright dots, and there's the spectral curve. Now, this guy was in his mid-20s. I sort of stared at the postage stamp view of your room earlier, trying to see if there was anybody in their 20s there. I couldn't discern that. Young guy. And there's a beautiful account on my site. And I can point you to it if you want to contact me via our contact form, where he is interviewed and describes this discovery. This was something really bright, and they didn't know what it is or was. And he looked at all these lines, and he couldn't figure out what they were. So like any good scientist, he said, well, let me compare these unknowns to a known. So he looked at the hydrogen bomber lines. There's that robin egg blue one we've seen before, hydrogen beta line. And he went, well, I guess it's not hydrogen I'm seeing, because I don't see any of these lining up with my data. So, there's no great line. There's no match, except there was massively redshifted. And he figured it out. He went home that night and he told his wife, something terrible happened at work today. And he describes this in this transcript on my site. And his wife said, well, you're drinking champagne. You don't normally do that. What was bad? And he said, I made a discovery, and I'm worried that in the future, I'm not going to get peace and quiet because I'm going to be famous. Now, these days, of course, he'd be on TikTok making his announcement, perhaps. But he was fortunate that he was recognized for his accomplishment, but didn't become the kind of famous that interfered with the research that he did. So Adam Rees, the Nobel Prize winner, commented on this spectrum when I submitted it to Sky&Telescope, and it was published there. And like I said, I'll tease you a little bit. If we have time, we can talk about that. So the amazing thing to me is that we are able to calculate the redshift with a backyard telescope, that these photons have enough energy, these waves have enough energy to cover that distance and carry information over 2 billion light years in time. Time gets a little weird, but we'll talk about it that way. Unfortunately, there are other things in the universe that don't age quite so well. There's Martin Schmidt a few years ago. He's since passed away, and I've been justly accused of throwing him under the bus, and it's true. He's got a full head of hair here. I'm envious of the guy. Give me a break. So I have one or two more examples, but I wanted to show you this example on this next screen, because for those of you who are doing outreach or want to do outreach, this is the kind of thing that not only does it win science fairs, but more importantly, it helps young students grow, and you can do that. This topic is really popular with chemistry teachers, because they like to have these cross-cut, they're called, topics where even though they're studying chemistry, they're also doing some astronomy. And with gas tubes, most chemistry teachers use gas tubes. You can go in and do a presentation of this sort, and also then do a live viewing one evening near the school. So this is a cool little project, and you don't have to be a rocket scientist or an astrophysicist to coach people on this. I just reviewed a student's work in New Zealand last night, in a STEM course, and I'm working with a young woman in Provo, somewhere in Utah. I forget where in Utah. A really bright woman, and as a high school student in Switzerland. These people come to me, and you can fish these people out of your local population and really just have a great time doing it. Okay, I've got two more examples here for you. So far, we've been looking at, these hydrogen bomber features. How wide are they? They're what, about 50 angstroms wide, like I said there. What if we want to zoom in on this bad boy? What then? Well, then we need one of those slit devices that I mentioned earlier and showed you an example of. Here's Vega, and here's the moon. Now, the moon isn't really moving towards or away from us, but Vega is. So with a slit spectrometer, one of those, several $1,000 devices, you can calculate and detect the radial velocity of that object. It's pretty amazing. Fairly advanced work, but it's not that hard to do once you have a good foundation. So this is the final example I have for you, and then we'll finish up. We have a couple more minutes. And that is Vega. Now, I've got a visual aid here. I'm hoping you'll be able to see it. So I'm going to actually stop sharing my screen. Here's a star, right? It's rotating. So this edge, where this hand is coming towards you, right? And this edge, as it rotates, is moving away from you, right? And there's somebody peering out from behind the star. So this light is coming towards you. It's blue. I forget which way I had it rotating. One is blue shifting. The other is red shifting. So let me share my screen again, and we'll do that. Give me a second. Get my mouse going, share my screen. There it is, and then the slideshow. There we go. So this is what I just showed you, right? The rotation of the star itself, if it's big and fast enough, is going to be causing red and blue shift. So when we study a star that's spinning fast, look how that nice tight dip on slow rotating Vega is smeared out by that shift. It's incredible that people have figured out how to do this. Okay, how do you get started? Well, I already mentioned the star analyzer grading, some sort of camera, almost any camera. We have tools on the site, and I can work with you to assure that the star analyzer fits your system. You need some sort of software. You've already heard about RSpec Mine. This is some freeware that's out there, a little tough to get started on. There are actually some others. And you may need just some sort of spacer, because this distance here, while not critical like focus, needs to be within range. There are tons of books. I just wanted to show you this briefly. These are detailed on my site. I'm happy to talk with you about these or anything else. These are those practical astronomy books from Patrick Moore. Now, you may be familiar with them. They're very accessible. They're thin. They're inexpensive. You don't need to do a lot of math or any to read those. We have a great online site where questions get answered often by people like me and others, so many of whom know more than me. The software is free for 30 days. We have a tutorial. The AAVSO has a database that you can contribute to in Spectra. They don't only do photometry, they do Spectra too. Lauren Harrington heads up that database, really great, originally a star analyzer user. And she's now working with Sarah Seeger at MIT, a well-known astronomer. So we really all are excited for her and the start that we gave her with the star analyzer. You can download our free software and watch the workshop that I gave to the AAVSO. There's sample data on our site. I can help you with all this. There are opportunities for pro-am collaboration, but I have to admit they're not as frequent as one might like. There's more coming, we hope, through the AAVSO and others. Everybody on this line are amateurs, and then Bob Stencil, University of Colorado, is a professional there. So we've come a long way since the HR diagram 45 minutes ago. Again, like my wife and her maps, her paper maps that she didn't have and was lost, I felt lost until I began to understand the HR diagram with the help of Spectra that I was capturing. It's a fantastic opportunity for you. it's hard for me to relax and just say, do it if you want. Yeah, I'm a businessman. That's true. But this is now a labor of love. And as you all know from hearing the yelps of delight and the quiet smiles of people observing their first Saturn rings, this is a new place you can discover something new and exciting. And I encourage you to jump on board. As I said, we've come a long way since Fraunhofer, and they first discovered the lines in the sun. And I want to thank you for your attention tonight. And thank you all for doing the outreach and the giving back that you do. Thanks again. Oh, what happened to my focus? That's awful.
Thanks, Tom. I'm polling the room to see if anybody's got any questions. Yeah, should be able to. Hey, Tom,
Hi.
we're going to get you a question in the room.
Good. I'm going to try and get this camera to give me some skin tone.
You're getting there.
Push the button. No.
Hi, Tom. Doug Lively, Raleigh Astronomy Club.
Hi.
There's a lot of talk and excitement around T Corona Borealis. Just wondering if you've had a chance to do some studies yourself and if you've got anything you might want to share with us.
Oh, that's a great question. Amateurs are all poised. They're capturing before images now. I live in Seattle, so trying to capture data is sort of a fool's errand. I'm well qualified for that, but I don't do that much these days. But amateurs are expecting to see some really exciting spectra with emission lines. And I think we will be in a position to contribute, not because we've got lots of aperture and high res equipment, but because we're everywhere. That's a good question. I wish I had more answers for you, but we'll see hopefully in the next maybe 5 minutes or 5 months. Who knows?
Any questions online? Any more questions in the room? All right, Tom, we'll let you go. Here, I'm going to hold
Great.
the mic up so we can clap for you, okay?
There you go. Good evening, everybody.
Thanks. Thanks, Tom. Have a good night, sir.
You're welcome. You all too. Stay safe.